Okay, let's go ahead and look at the relationships that you should have discovered for the relationship between mass, distance, and the force of gravity. So there were two different experiments that you're responsible for understanding. One of them was the relationship between mass and force of gravity, and the other is between the force of gravity and distance. Now I'm going to generally say force of gravity, but remember the force of gravity and weight are the same thing. Mass is different, okay? F of g and weight are both vectors. They both deal with the force of gravity, which can change based on mass and distance, okay? If we look at the graphical relationships between these, you should have discovered probably in the peer review session that the relationship between f of g and mass is a direct linear relationship. So we do have a 0, 0 intercept. You should have been able to discount your y-intercepts from error, okay? The relationship between f of g and distance is different, okay? It's, I think this is called a hyperbola. This would be an inverse square function, or sometimes it's called a reciprocal square function. If we needed to find a generalized equation, we would have to linearize this, okay? So in terms of verbal descriptions, what do those mean? For the first one, f of g is proportional to mass, and I've shown this proportionality with a proportional statement. So f of g is proportional, that's what the symbol means, to mass, and so if mass doubles, f of g doubles. So if you have half of f of g, then the mass must go down by half as well, according to this relationship. The f of g and distance graph was a little bit different. This proportionality was to the square, or the reciprocal square, so f of g is proportional to 1 over d squared. So if we're thinking about doubling distance in this case, if we double the distance, what happens to our weight? And I set up a little data table to help me figure this out, and I put force of gravity is equal to 1 over distance squared, okay? So if d is 1, 1 squared over 1 is going to be 1, so f of g is 1. Now if I double that to 2, then I have 1 over 2 squared, which is going to be 1/4. So notice when I double the distance, the weight, or the force of gravity, goes down by a factor of 1/4, which is pretty amazing, and really something to think about in terms of like how that works for like how that would work, like where on Earth, like how far away from Earth do you have to be for that to significantly decrease, and that's going to be something we're interested in looking at. So if we look at the y-intercept for each of these graphs, the y-intercept in the first one, so the mass versus, or f of g versus mass, should be 0, 0. Remember that we started by saying that if there is mass, then there is gravity. So this relationship proves that. If there is no mass, okay, if there is no mass, then f of g must be 0. So that's the physical significance of the y-intercept on the first one. The second one is a little bit different, okay? We have f of g versus distance. So if you'll notice, these two actually never, they will approach the x and the y axes, but they'll never actually get there. So these are called asymptotes, and what this means is you really never leave a gravitational field, because no matter how far away you go, it just keeps getting smaller and smaller and smaller. In the reverse over here, no matter how close you get, the closer and closer you get to two particles, the force is just going to grow and grow and grow and grow. And so we can really think about, even at the electron level, no matter how close you get those electrons, there's still going to be some gravitational attraction. Okay, let's go ahead and tackle the the generalized equation. And I'm not going to cover slope, because the slope analysis is a little complicated for this, and after we talk about the generalized equation, you should see kind of the meaning of what your slope was, all right? So the generalized equation, if you actually take the two experiments together, and I've said 3 because some people chose to investigate mass 1, some mass 2, and others distance. But if you smash all of those together, you actually get one giant equation, and this says f of g is equal to big G, okay, capital G, m1 times n2 divided by distance squared. So you can probably see these things. I mean, we said f of g was proportional to d squared, or 1 over d squared, and f of g was equal to the mass. We've just got the product of the masses now. So what is this g? Okay, this g is called big G. It's the universal gravitational constant. It's the same everywhere in the universe. This is not little g, which you may know as 9.81 meters per second squared. Totally different, okay? This big G value is always the same, and that value is 6.67 times 10 to the negative 11th. The units are newtons meters squared over kilograms squared. And notice that this number does have units attached to it. Okay, we're not plugging in for those. Those are units that are attached to that. So what exactly does that mean? And was big G actually in your experiment? And the truth is, it was, okay? So the big G showed up in your slope. If you look at the value of your slope, they're probably really small, okay? And if you did like one of the masses, you probably had your generalized equation as f of g is equal to k, which is your slope, your constant of proportionality, times n1, all right? If you did the other one with distance, you got f of g is equal to k over distance squared. Now, if we were to look at that k value, we would actually find for this experiment that big G times whatever your mass of mass 2 was divided by your distance squared, so how far away your two masses were. Remember I told you to keep track of those values. You would find that that value is actually equal to your slope, okay? And over here, if you took your two masses, you held your two masses constant. If you multiplied those two masses in kilograms together times big G, again, you would find your slope. So that's pretty cool. I highly suggest you check that out. This is one of the things that makes physics so awesome, is that almost always the things that you keep constant in your experiment show up in your slope, okay? Just a side note, when you work calculations with this large equation, okay, notice that I've just rewritten the equation. F of g is equal to big G m1 m2 divided by distance squared. I've plugged in, here's my G value, newtons meters squared over kilograms squared, okay? Times m1, which I said was 14 kilograms, times m2, and then divided by my distance squared. Notice that these kilograms, okay, kilograms times kilograms will be kilograms squared. They're going to cancel down here. And meters squared is going to cancel with this meters squared. I'll be left with newtons, which is the units of f of g. So it's important how to know, or to know how to use big G, okay? Last thing that we're going to talk about today is the assumptions of the model. The assumptions of the model is that gravity is a force. Okay, Newton defined gravity as a force that acts in a field. So in other words, you don't have to be in contact with, for example, the planet to feel the forces of gravity. That's why we say it's a field or a non-contact force. But that was Newton's idea. Einstein came along later and talked about space-time and gravity being more like a wave and behaving like a wave. So I really encourage you to look up gravitational waves. This model, the model that we developed, would not work for predicting gravitational waves.